Welcome to The Explainer. Today, we're unpacking the fundamental vocabulary of electricity. We all toss around terms like current, voltage, and EMF pretty much all the time, but getting their exact definitions straight is absolutely crucial. So we're going to solidify these foundational concepts together, keeping it clear, visual, and right to the point. Here's our roadmap for today. We'll be hitting electric current, flow direction, potential difference, electromotive force, and finally wrapping it all up by comparing EMF versus potential difference. All right, let's jump right into part one, the flow or electric current. So what actually is electric current? By definition, it's the rate of flow of electric charge through a conductor. Now, the absolute key phrase here is rate of flow. It's not just that the charge is sitting there, right? It's about exactly how fast it's rushing through the wire. And we represent this flow with the symbol I. Let's quickly break down the math. It's I equals Q over T. So I is our current, which is measured in amperes. That's driven by Q, which represents the electric charge measured in coulombs, divided by T, which is just time in seconds. To put it simply, current is literally just the sheer amount of charge divided by the time it takes to flow past a specific point. To put that into perspective, what really is 1 ampere? Well, it's actually a beautifully simple 1-to-1 ratio. 1 ampere is exactly 1 coulomb of charge passing through a conductor in exactly 1 second. Boom, that's our standard unit. And you know, this whole flow of charge thing, it's doing the heavy lifting literally everywhere around you. It's what's flowing through the glowing light bulbs above your head, it operates your ceiling fans, powers your TV, and it's running through the charger keeping your smartphone alive right this very second. Moving on to part 2, we have a bit of a historical quirk, flow direction. Okay, let's talk about conventional flow. This is defined as the assumed direction in which positive charges move in an electric circuit. According to this convention, electricity flows out of the positive terminal of a battery, runs through the external circuit, and goes right back into the negative terminal. But keep a close eye on that word assumed. Because here's the crazy part. Scientists adopted this positive to negative direction way before they actually discovered electrons. Once we finally did discover them, we realized, wait a minute, electrons are negatively charged, which means the actual flow of electrons is moving from negative to positive. It's wild, but because of this massive historical mix-up, the old convention just kind of stuck. We still use conventional current for circuit analysis today, even though the actual physical electrons are moving in the exact opposite direction. So, okay, we've got our flowing charge, and we've agreed on which way to draw the arrows on our diagrams. But that leaves a pretty massive question hanging in the air. We know charge moves, sure, but what actually does the work to push it? I mean, charge doesn't just get up and move on its own. That brings us perfectly to part 3, the push, also known as potential difference. The official scientific term for this push is potential difference, though you probably know it better as simply voltage. By definition, it's the work done per unit charge in moving a charge between 2 points in an electric circuit. It's represented by the letter V. Notice I'm really emphasizing between 2 points here. It specifically measures the exact amount of elbow grease, or work, required to get from point A to point B in your circuit. Looking at the formula, we've got V equals W divided by Q. Here, V is our potential difference in volts, W is the work being done, which is measured in joules, and Q is, once again, our charge in coulombs. So voltage is basically just joules of work divided by coulombs of charge. Easy enough, right? And just like we did with the ampere, let's make this super concrete. Exactly what is 1 volt? Simply put, 1 volt is the potential difference when exactly 1 joule of work is done to move 1 coulomb of charge. Think about the sheer scale of this push in stuff you use every day. A standard AA battery, that only gives a tiny 1.5 volt push. A big, heavy car battery delivers a much stronger 12 volt push to get an engine cranking. But the electricity coming straight out of your wall socket, now that delivers a massive 220 to 240 volt push, depending on where you live. The higher that voltage goes, the more work is being done per unit of charge. All right, part 4, the source, or electromotive force. So this introduces a term called electromotive force, commonly known as EMF, and we represent it with an E, or the Greek letter epsilon. EMF is the total energy supplied per unit charge by a source to move charge around a complete circuit. Now, the absolute key distinction here is total energy for a complete circuit. We are zooming way out to look at the entire capability of the battery itself, not just a random journey between two arbitrary points on a wire. But wait a second, look at the formula for EMF. It's exactly the same. EMF equals W divided by Q, joules of energy supplied divided by coulombs of charge. And guess what? Its standard unit is also the volt. Because both of these concepts share the exact same formula and the exact same SI unit of volts, they are incredibly easy to mix up. Which perfectly sets up Part 5, EMF versus potential difference. Let's just clearly map out these distinctions so we never get them confused again. First up, energy. EMF is the total energy supplied by the source, whereas potential difference is the energy actually used between two specific points. Second, the circuit state. EMF is measured when the circuit is completely open and no current is being drawn. It's like the perfect ideal state. Potential difference, on the other hand, is measured when the circuit is closed and current is actively flowing. And finally, voltage level. EMF represents the absolute maximum possible voltage of your source, but the potential difference you measure in a real-world circuit, it's almost always a bit less than that due to the battery's own internal resistance. And honestly, that brings us to a really fascinating thought to leave you with. If a battery is rated for a specific maximum EMF, but the actual potential difference pushing your current is always a little bit less because the battery itself is resisting the flow, how much energy is your circuit actually getting? Unlocking that hidden loss of efficiency through internal resistance is totally the secret to mastering real-world electronics. But hey, that is an explainer for another day. Thanks so much for learning with us today.